you want, you can screen share. So good morning to everyone. It's our pleasure to have Visakan Balakumar from the University of Sheffield that today is going to present to us a work that will show us about the interplay of superradiance and the quantization of interacting fields in charged or rotating spacetime. So I leave you the stage to you, Visakan, and thank you so much for accepting our invitation.
Thank you for the offer of giving a talk, and thank you for Nunu, my friend, who is, I believe, also here, who helped set this up. So, hola, everyone, tudo bem? I won't attempt any more Portuguese. I went to France on vacation last week, and when I arrived, it was only Portuguese that was coming out. Now I've got the opposite problem. When I try to speak Portuguese, it's only French. So I'll leave the Portuguese there. But good morning, everyone. So I'm going to talk about some work that I did with Professor Crispino, who's on the call, Dr. Rafael Bernard, who are both from Pará University in Brazil, and with my supervisor, Elizabeth Winstanley from Sheffield. So before launching into the talk, originally I wanted to talk about a few different states, and it was quite heavy on the QFT side. And then I realized that the interests in Aveiro are probably more to do with superradiance. So I'm really going to sort of focus on black hole superradiance in this talk. But a sort of different situation. I think the one that's more studied is superradiance in Kerr spacetime. I'm going to talk about superradiance in Reiser-Nordström spacetime. So the first thing is, this is within the broad scope of quantum field theory in curved spacetime, and trivially, this is an extension of standard QFT to Lorentzian manifolds. It can be thought of as a first-order approximation to quantum gravity. So things like some of the major effects in major things that we know a quantum theory of gravity should have, such as black holes emitting thermal radiation, Hawking radiation, have come from the study of QFT in curved spacetime. There's an interesting discussion in the beginning of the book by Birro and Davies on the sort of limits of validity of QFT in curved spacetime. So I'd refer the interested reader to that book. But really the core kind of equations that we're going to be interested in is Einstein's semi-classical field equations. This really encapsulates QFT in curved spacetime, because on the left of the equation, you can see that we leave the background spacetime classical. And on the right, we quantize the field, the matter within the spacetime. And that's described by this, the quantum expectation value of the stress energy tensor. Now, as I briefly outlined in the introduction, what we're particularly interested in is black hole superradiance. And that's been well studied in Kerr spacetime, where superradiance arises due to the interaction of the field, which is co-rotating with the black hole. Now, there's a parallel situation in Reiser-Nordström spacetime, which is charged superradiance. And this comes about because of the interaction of the scalar field charge and the charge of the black hole. Now, why study charged superradiance in Reiser-Nordström spacetime? Well, Reiser-Nordström spacetime is spherically symmetric, and it's in some sense the simplest spacetime which exhibits superradiance. So the more we learn about charged superradiance in Reiser-Nordström spacetime in the absence of rotation, will help to disentangle whether it's superradiance or whether it's the fact that the spacetime is rotating in Kerr that inhibits our ability to define quantum states with the same sort of understandings that they have in Schwarzschild spacetime. So this is a sort of very basic diagram of black hole superradiance. So it's the incoming wave is scattered and reflected back with a greater amplitude, charge amplitude in the case of Rise and Nordstrom spacetime. Not sure what's happened. Oh, there we are. So firstly, just a bit on the classical situation, the background geometry. So Rise and Nordstrom's solution has a geometry that's described by the line element in equation 2. So structurally very similar to Schwarzschild spacetime. The metric function just has this extra q squared over r squared term in comparison to Schwarzschild, where q is the charge of the black hole and m, of course, denotes the mass of the black hole. Now, we will only consider in this talk the sub-extremal case where the square of the mass is greater than the square of the charge. And in that case, the metric function has two roots, where the one root is the location of the black hole event horizon and the other the inner Cauchy horizon. Now, I think in the extremal case, you have a naked singularity, and in the, yeah, I think that's the case, but we will only consider the sub-extremal case. And when doing so, the spacetime looks like this. So this is a Penrose diagram of the Rise and Nordstrom spacetime. Now, we'll mainly focus on region 1 in this talk. Sometimes it's useful to consider region 4 in order to define certain quantum states, but I'm going to just try to talk about superradiance in today's talk, and therefore will only be considered by region 1. Some important, can you see the cursor moving?
Yes, we can see it.
Okay, great. So this surface here is the past null infinity. And this surface here is future null infinity, the future horizon, and the past event horizon. So those are 4 important surfaces which will come up repeatedly in this talk. So now we're going to study the dynamics of a field, a classical field for now on this spacetime. So if we have a classical scalar field, then its dynamics is described by equation 5, which is the Klein-Gordon equation or the scalar field equation. And these big D's are the gauge covariant derivative, which is given here. And the gauge potential, mu, has this form here. So we've just got this term in, it's just got an AT component, which is equal to this here. And now we've set this gauge potential to vanish at infinity through a choice of integration constant. And that means it's got quite a natural interpretation. And the frequency that an observer would measure far away from the black hole. So this equation can be readily solved by a separable solution of the form here. And we have the following quantum numbers, omega, L, and M, and M usually running in its usual range. This angular function here is actually a spherical harmonic, which we would expect because Rise and Nordstrom spacetime is spherically symmetric. And it's just got the sort of usual normalization, which isn't too important for this talk. So we can, the physics is really contained in the radial part of this equation. And we have the usual Reggie Wheeler equation with an effective potential. Here, I'll point out that this is the tortoise coordinate defined in the usual way. So we can derive this effective potential by solving the radial equation, and it looks essentially like equation 8. And what's important is it takes asymptotic values, different asymptotic values, near the horizon and at infinity. So in particular, near the horizon, it's got this sort of modified formula where we see the scalar field charge and the charge of the black hole. And this is what really gives rise to superradiance, these different sort of asymptotic forms of the scalar field effective potential. Now, we've defined the quantity omega tilde here, just as a neat way. So omega tilde is the asymptotic form of the effective potential near the horizon, and omega at infinity. Now, in order to study this situation, it's quite useful to come up with an orthonormal basis of solutions to the radial equation. And you might or might not have heard of these before. We will introduce the in and up scalar field modes. So physically, the in mode has unit flux coming up from past null infinity, and some of it goes down the future horizon and some of it is scattered towards future null infinity. The up, on the other hand, has unit flux coming up from the past event horizon, with some of the mode going towards future null infinity and some being scattered back down the future event horizon. Now, for the purposes of this talk, it's also useful to consider the time reverses of the in and up modes, and we denote these the out and down modes respectively. So in effect, these are essentially the complex conjugate of the in and up modes as written here, and they have the following forms. So the down modes have unit flux going down the future event horizon, and the out modes have unit flux going towards future null infinity. We need to in order to quantize this system, we need to normalize the field modes. And in order to do so, we employ the Klein-Gordon inner product, which is defined in equation 12. Now, in the integral, you can see the symbol sigma, which essentially corresponds to a Cauchy surface. Now, the actual normalization constants are independent of the choice of the Cauchy surface over which the integral is performed, which means that we can choose essentially a very convenient choice of Cauchy surface. So in order to normalize the in modes, for example, the in modes vanish close to the past event horizon, but they have unit flux near the past null infinity. So what we would do is choose, and the converse is true for the up modes. So what we would do is choose a Cauchy surface close to the union of the past event horizon and past null infinity. And there's a similar process for the out and down modes. What's interesting is that we find different normalization constants for the in and out modes on one hand and the up and down modes on the other. The in and out modes normalization constant is proportional to omega, which appears in the scalar field effective potentials asymptotic form far from the black hole, and the up and down modes, which are non-zero near the event horizon, their scalar field effective, their normalization constants are proportional to omega tilde, which appears in the scalar field effective potential near the black hole event horizon. So again, I'll just remind that everything we're doing so far is just classical. So we can use the radial equation to derive the following useful Wronskian relations. And it's quite simple to derive these, so I won't go into too much detail. But essentially, we have equations 14 and 15. Now, the interesting physics happens when we sort of interpret the A omega L and the B omega L as reflection and transmission coefficients associated to the field modes, respectively. And when we do so, we can observe classical charge superradiance. So looking at equation 15, you can see, not equation 15, equation 14, you can see that a scalar field mode which has omega times omega tilde is less than 0. So in effect, they have the opposite charge, the opposite sign, omega and omega tilde. will have the square of their reflection coefficients greater than 1. And so this effect of superradiance happens when an ingoing field mode, which has opposite signs for omega and omega tilde, will be reflected with a larger amplitude than it was incident with. And thanks to the nice plots that Dr. Raphael Bernard came up with, we've got this plot here in figure 1, or that should be labeled, apologies. And we've chosen the ratio of the charge of the black hole to its mass to be 0.8, and then plotted this for various values of the scalar field charge. Now you can see the black line here is when the scalar field charge is 0. And of course, there's no superradiance. There's no superradiance because there's no interaction between the scalar field charge and the charge of the black hole. So there's no amplification here, as we would expect. As we increase the scalar field charge, we see greater and greater levels of superradiance. And what's interesting about this is actually the wave amplification is much larger than in Kerr. So that's already in the classical case, we see that charge superradiance is a much stronger phenomenon than rotational superradiance in Kerr. So now we would like to quantize this system to study it, study the quantum mechanics of it. So what's interesting about curved spacetime is there's no unique vacuum state in curved spacetime. And there's 3 sorts of major vacuum states in Schwarzschild spacetime. There's many more in Kerr and Riese-Nordström. I think in our paper, we defined 9 in total. The one I want to speak about today is the Bowler state, because that corresponds most closely with our familiar notion of a sort of empty state for an observer at infinity. Now, in Riese-Nordström and in Kerr spacetime, as we will see in this talk, you can define 2 separate Bowler states, defined one for an observer at past null infinity and one for an observer at future null infinity. And we'll refer to these states as the in and out vacuum states, respectively. Now, in Schwarzschild spacetime and in the absence of superradiance, we would expect these states to be essentially the same. And the way that we would prove that these states would be the same would be that the expectation values of the observables that we're interested in this case, the scalar field current and the stress energy tensor, would be the same. And so we can really use these in and out vacuum states that you might hear these referred to as the past Bowler state and the future Bowler state in the literature, as a tool to explore superradiance in the Riese-Nordström scenario. So we choose to quantize via canonical quantization, and this, what they don't teach you in QFT courses, but is quite interesting, is that this relies on decomposing the field into a set of positive frequency modes and a set of negative frequency modes. But if you remember back to the slide when we were evaluating the normalization constants associated to the in modes and the out modes on one hand and the up modes and the down modes on the other, the in modes have positive norm when this quantity omega is greater than 0. And the up modes have positive norm when this quantity omega tilde is greater than 0. So it's difficult, in fact impossible, to define a set of positive frequency modes which are positive frequency with respect to both omega and omega tilde at the same time. The best we can do is equation 16, where we decompose the in modes with respect to omega into positive frequency and negative frequency modes here, and the up modes with respect to omega tilde here. And once we've defined that and expanded the field in equation 16, then the operators will have the following canonical commutation relations with all other commutation relations not explicitly written here vanishing. Just something that's quite important to draw your attention to. So these are for omega is greater than less than 0, sorry. These are for omega tilde is less than 0. So we will denote the in state like so, and we can define it by requiring that it's annihilated by the A in and the B in up operators. So what this really physically corresponds to, if you remember back to the Penrose diagram, is a state that is as empty as possible at past null infinity. And it contains no particles which are outgoing from the past event horizon. So very much in the past of the black hole, there's no radiation observed by someone at past null infinity. And we want to see whether this state is exactly the same as the out state for an observer at future null infinity. So to do so, we'll essentially repeat the process in terms of the out and down modes. So I'm not going to go into too much detail, but this is essentially how you would define the state for the out and down modes. It's essentially the parallel of the previous two slides. The out vacuum is as empty as possible as seen by an observer at future null infinity. And it also contains no particles ingoing at the future event horizon. So I'm just at the halfway point. So I'm curious as to, okay, so the time is not bad. So that's fine. So in order to sort of investigate these two states further, what we need to do is to look at the expectation values, the quantum expectation values of the relevant observables. Now, we would normally be interested in the expectation value of the scalar condensate, and the scalar condensate is defined as so. As you can see, it's the square of the field. And given that the in and up states were, that is wrong, this line here, apologies. The in and out are complex conjugates of each other, and the up and down are complex conjugates of each other. So the scalar condensate, which is a scalar quantity and is proportional to the absolute magnitude, won't be able to distinguish between the in and out states because they're defined as complex conjugates of each other. So we can't investigate the difference between these states using the scalar condensate. Instead, we'll have to focus on the scalar field current, which is defined in equation 22, and the stress energy tensor, which is defined in equation 23. And we can write these expectation values of the current and stress energy tensor in the following asymptotic way. So these are the mode contributions associated with the field mode. And don't worry too much because I know there's a lot of long formulae, but I'm just showing you the mechanics of how it works. So as you can see, there's quite a lot of individual components, so it's easier to consider these tensor operators on a component basis. We write these expectation values as a sum of field modes, and so we essentially need to work out the individual field mode contributions to each component. Now, it turns out that the current has only two non-zero contributions, and that's to its T component and to its R component. And the label K here refers to whether it's an in, up, out, or down mode that we're considering. So again, if you look at the T component, you can see that it's just proportional to square magnitudes of things. In particular, the radial function here is only seen as a square. And so that means that the expectation value of the T component of the current won't be sensitive to the difference between the in and out states, since they're complex conjugates of each other. But this isn't the case for the R component, and the expectation value of the R component of the current is a flux, as we'll come to see later. There's a similar situation for the stress energy tensor. The TT component is non-zero, as is the TR, RR, the theta theta, and the phi phi. But again, you can see if you look at the radial parts of the diagonal components of the stress energy tensor, the TT, the RR, the theta theta, and the phi phi, they're both proportional to absolute magnitudes. So again, they won't be able to distinguish between the in and out states. So really, again, it's this flux component which is contained in the TR component of the stress energy tensor, which is really interesting and will reveal to us whether the in and out states are the same. And so we're going to focus our attention on these two components, which are the flux components. Now, we've proven in an earlier paper that expectation values of the current operator in any quantum state are conserved. And so we can integrate the R component of this equation. And for the static states that we're considering in this talk, this gives the following equation. So the expectation value of the R component of the current is proportional to some constant minus some constant over R squared. And this constant depends on the quantum state under consideration. Now, if we're to physically interpret kappa, that would be the flux of charge, which is flowing from the black hole. And when kappa and the charge of the black hole have the same sign, then the black hole is losing charge. If they have the opposite sign, then the black hole is gaining charge. If we're to look at the RT component of the stress energy tensor, so just before I get onto that, again, in an earlier paper, we have to remember that there's two fields in this setup. So there's the scalar field, which we're considering, and there's a background electromagnetic field. Now, if we consider the total stress energy tensor of both the background electromagnetic field and also the scalar field under consideration, then the total the total stress energy tensor would be conserved. Now we're just considering the classical scalar field, the scalar field that we're studying, and so the stress energy tensor associated to it is not conserved, but instead has this expression contained in equation 31. And F mu nu is the background electromagnetic field strength tensor. So again, for the static states that we're considering, the T component of equation 31 can be integrated to give the following expression in equation 32. And if you remember, kappa is the flux of charge from the black hole. So this new constant L, it depends on the quantum state under consideration, and we can interpret it as the flux of energy flowing from the black hole. And when L is greater than 0, the black hole is losing energy. And now we can sort of derive these relations between the expectation values of the components, the flux components that we're interested in, using the fact that the out modes and the down modes are the complex conjugates of the in modes and the up modes respectively. And so the expectation value of the current and of the RT component of the stress energy tensor should be in the out state should be equal and opposite in its sign to those in the in state. So what this slide is essentially telling us is that we only really need to calculate the expectation value in the in state. And if it doesn't vanish, then we know that there's superradiance occurring. We have subsequently published this proof in a more recent paper, But essentially the flux components, these components do not need renormalization. So we can simply evaluate their expectation values immediately. And using the asymptotic forms of the field modes, we find the following quite complicated expressions for the expectation values of the flux components in the in-state. Now, these are quite complicated and involve sums and integrals. The important thing essentially is that they're non-zero, clearly. So the in and out vacuum states are not the same, and there is superradiance occurring. So what's interesting, if we look at these integrals in a bit more detail, is that we only find that the up modes contribute towards these integrals. And interestingly, we only find these intervals, which essentially are telling us that it's only the superradiant up modes which are contributing to the flux of charge and the flux of energy from the black hole. So this is really telling us that the only reason that we can't define a state, a Bowler state, which is non-zero, which is as empty as possible to an observer, both at future and past null infinity, is due to these superradiant up modes. And it essentially corresponds, so what an observer, a static observer far away from the black hole would see is this outgoing flux of charge and energy. Now, what's quite interesting is classically superradiance is sort of a stimulated effect. So a wave comes in and it's reflected with a greater amplitude than it was incident with. Now, when we quantize the system and study it quantum mechanically, it's a spontaneous effect. So the black hole is spontaneously emitting particles in the superradiant modes. And this is the phenomenon of quantum superradiance in the Reisen-Nordstrom case. Now, we can, using the expressions derived earlier, we can evaluate the constants K and L, which are the flux of charge and the flux of energy, respectively. And if we look at the form of equations 35A and 35B, there's no thermal factor. So what that means is that the flux due to superradiance is a non-thermal distribution, and it's separate from the Hawking radiation. It's not the same as the black hole emitting Hawking radiation when it's quantized. Now, we're studying the massless case, but just for completeness, if the field had a mass, then these fluxes would be suppressed by an exponential factor. So now, so that was things that we did just analytically in the asymptotic cases. Now I'm going to talk about the numerical work, and that was really done by Dr. Raphael Bernard in Paris University. So if you remember back to the radial equation, how we essentially study this system numerically is integrate the radial equation, which contains the form of the effective potential. And that allows us to calculate the expectation values for the rate of for not just the radial coordinate close to the horizon or far from the black hole, but all values of the radial coordinate. And as usual, we plot the components for Q is equal to 0.8 times the black hole mass and several different positive values of the field charge. So what we get is the following. Now, remember, I defined the flux component, the expectation value of the R component of the current to be equal to minus this constant K over R squared. So if we plot R squared times the expectation value of the R component of the current, we should have a constant K. And that's what we observe here. That's this red dotted line. Now, what's interesting here, and does not actually occur in Kerr, and I'll talk a bit more about this later, is the quantity R squared times the RT, the expectation value of the RT component of the stress energy tensor. Now that's negative for large values of R, but it's actually positive very near the event horizon. Now that's not seen in Kerr spacetime. And this is in the in state. So if we just focus on the flux of charge for now, if we plot the flux of charge against the scalar field charge, we can see that as the scalar field charge increases, the flux of charge increases quite rapidly. And the flux of charge and the black hole charge have the same sign, which means that quantum superradiance causes the black hole to lose its charge, to discharge. And the higher the scalar field charge, the more rapidly the black hole loses its charge. Now, if we consider the expectation value of the RT component of the stress energy tensor, we see that the black hole is always losing energy due to superradiance. So this corresponds to a loss of black hole mass. And again, the flux of energy from the black hole increases as the scalar field charge increases. So the higher the scalar field charge, the more energy that the black hole is losing. As we can see due to these lines plotted here. Now, just analyzing this a bit more. So if we look back close to the horizon, the expectation value of the RT component of the stress energy tensor is positive everywhere. And that's due to the second term in equation 32. I'll just quickly go back to that. Due to this term here in the definition of the expectation value of the RT component of the stress energy tensor. Now, in Kerr spacetime, on the other hand, the expectation value actually has the same sign everywhere outside the event horizon. So that difference is quite interesting, and we can look into it a bit more. So at the event horizon, we find, in the Reise-Nordström case, we find a flux of ingoing energy rather than outgoing energy. And the magnitude of the ingoing energy increases as the scalar field charge increases. Also, the expectation value vanishes at this value of the radial coordinate, and therefore the flux of energy vanishes at that coordinate. And this value of the radial coordinate is positive, so it's essentially outside the event horizon for all non-zero values of the black hole charge. And this seems to indicate that this value of R0, where the flux of energy from the black hole is vanishing, is independent of the scalar field charge for fixed values of the black hole charge. However, long story short, this is essentially due to a loss of accuracy in the numerical calculation. So in this plot here, we've really sort of zoomed into the value of R0, where the flux of energy vanishes, and you can see that there's a slight variation, and R0 actually increases as the scalar field charge increases up to a saturation point. As we would expect, as the charge tends to zero, the flux of the expectation value of the RT component of the stress energy tensor vanishes everywhere. And this corresponds to R0 not being well defined in this limit. So just going back to the fact that the expectation value of the RT component of the stress energy tensor, which has opposite signs close to and far from the black hole, in the Reise-Nordström case, which it, just to remind you it doesn't in the Kerr case. This is quite reminiscent of the notion of an effective ergosphere. And so inside the effective ergosphere, the energy of a charged particle can be negative, as seen by an observer at infinity. And we can sort of understand this as a classical process of charge and energy extraction from the black hole, which we've sort of thought of as a charged analog of the Penrose process. So for a massless charged particle, which we're studying in this case, the outermost radius of the effective ergosphere is defined, is given as this expression in equation 37. So the radius of the ergosphere depends only weakly on the scale of field charge, and that's similar to the point at which the flux of energy from the black hole depends only weakly on the scale of field charge as well. So I've got a little bit of time. So I said in the abstract that I would talk also about the Unruh and the Hartle-Hawking states. Well, before that, I'll just say, so essentially we've studied the quantum analog of the classical process of superradiance for a scalar field on Rising-Nordstrom space-time. And we computed the expectation values of the black hole fluxes in the in-state, so in the past of the black hole, which is as empty as possible to a static observer past null infinity. And we saw that the superradiant emission of particles is non-thermal, and it works to lower the magnitude of the black hole charge as well as its mass. And we constructed its time, reversed the out state, which sort of it's as empty as possible to a static observer at future null infinity. And these two states don't coincide because of the phenomenon of quantum superradiance. That's different to the case in Schwarzschild space-time, where the Bowler vacuum is defined as empty as possible to a static observer at both past null infinity and future null infinity. And so what we can see here is that you can't define a Bowler state in Rising-Nordstrom with the same interpretation as Schwarzschild space-time. Now, we actually tried in a further paper to do so. And while we were able to define a state which had some of the properties of the Schwarzschild Bowler state, it was defined using non-standard commutation relations. And after some useful discussion with I've forgotten the name of the individual, but after some useful discussion, we realized that this might be because the state is sort of non-positive in nature, and then therefore violates some of the usual assumptions for positivity in a quantum state. Now, it turns out that you can define an Unruh state with the same interpretations as those in Schwarzschild space-time for this setup of superradiant scattering in Rising-Nordstrom space-time. And it's a similar story as with the Bowler state for the Hartle-Hawking state in Rising-Nordstrom space-time in the presence of superradiant scattering. It is possible to define a thermal state with some of the similar properties as the Schwarzschild Hartle-Hawking state, but again, because it was defined with non-standard commutation relations, we're not sure if that state violates the positivity assumptions on a quantum state. So yes, essentially, this is a study of the quantum mechanical properties of black hole superradiance in Rising-Nordstrom space-time. And thank you for listening, everyone.
Thank you so much, Visakan, for your interesting talk and for keeping the time perfectly. So now we have plenty of time for questions. So I ask people in the audience if they want to raise their hands and just speak up. I see Nuno already. Please, Nuno.
Hi, Liz. How are you? Sorry for not having said hello in the beginning. I was having some trouble with my connection. Can you hear me?
Yes, I can hear you. Hello, Nunu.
Okay.
Nice to see you.
It's nice to see you again, virtually, but well, it's nice anyway. So I have maybe two questions. Um, so you focus your study in the subextremal case, right?
Yes.
And actually, I guess that here in the plots you showed, you always chose the same value for the charge over mass of the black hole, right? 0.8 or something like that.
Yeah.
So can you do the same study for an extremal black hole? Or at least can you have a taste on the trends of the results as you go to extremality or not?
So I personally wouldn't have been able to draw any conclusions as to what happens in the extremal case based upon our study. And I think, although I don't want to speak on behalf of Luis and Raphael and Elizabeth, I think that the situation is similar for them. Interestingly, Elizabeth has a new PhD student who's actually doing this for the extremal case. From what I've spoken to them about it, it's quite difficult to define some of the states in the extremal case, and that's due to it being very difficult to normalize the field modes. I'm not aware of whether they've made any progress, but I know that they are studying the extremal case, so hopefully they might publish something soon. But I personally wouldn't have been able to draw any conclusions on the extremal case.
Okay, thank you. So my other question is about this instability you have in this setup when you include a cavity, right? When you have a Reisner-Nordstrom black hole and a charged scalar field inside a cavity, you can get an instability, right?
Yeah.
Can you study this with your approach or not?
Yes, I think we can. I mean, I think actually we're partway through it essentially. Do you mean sort of like a black hole surrounded by a mirror, which gives rise to an instability? Yeah, we're studying it. I mean, the first half of the construction, when we're constructing, quantum states by canonically quantizing field modes, follows through quite similarly. And we're at the process now, really, where we would like to sort of investigate it numerically and investigate the expectation values of components to see whether there's an instability in this case, but we haven't got there yet, essentially. Okay. But it's an interesting question and one that we're also interested in. So thank you, Nunu.
Okay, that's all from my side. Thank you.
Are there further questions in the audience? Opinion, comments? Haroldo, please, Haroldo.
Hi, Visakan. Thanks for the nice presentation talk. I have curiosity. So you mentioned that the black hole can lose mass and charge at some point, right?
Yeah.
So you are in a test field approximation, right? So these charged scalar field does not back react to the geometry, right?
Yeah, exactly. We're not really considering the effect of the back reaction of the charge field on the geometry. Yeah.
So my question is a curiosity in this direction. So is there an attempt to see the effects of the back reaction in this case? Because well, the conclusions are different from the quantum and the classical results, right? So Is
long
there an
story
attempt to see the back reaction in this quantum analog case of superradiance?
Yeah, I mean, unfortunately, no, we haven't looked into that yet. And I think the next step that we're trying to do, in a follow-up paper to this one, in a longer paper, we sort of defined 9 quantum states, and the way we studied them is that we studied the difference between the various states. So what we would like to do is to study them directly by actually renormalizing instead of considering the difference between the states. So when you consider the difference between 2 states, the geometric divergences cancel, and therefore there's no need for renormalization. Now Elizabeth and I developed the Hadamard renormalization for charge fields, and that's I suppose the actual application of that to problems such as these is probably in its infancy. So that really is probably our next step, as opposed to considering the back reaction. But yeah, I agree with you. I mean, that looking into the back reaction would definitely be a very interesting avenue to take forward this research.
Oh, okay. Thank you, Visakan, and it's nice to see you.
And likewise, Haroldo.
Someone else with some curiosity or doubts or questions? Well, I have a couple in case no one else shows up more. But one was just asked by Haroldo. So the second one links with what the second question of Nuno. So there's some years ago, 5 years ago, some colleagues from Lisbon came up with some kind of violation of the cosmic censorship when you place a Reiser-Nordstrom charge scalar field within an ADS spacetime. So they found that there is an interplay between the decay of each of the modes that gives you some new family. So you have on the side superradiance, and on the other you have some family associated with the boundary condition at the DS. So this reminds very much of your black hole in a cavity, the Reiser-Nordstrom scalar field, and they find instabilities such that also you can have violation of the cosmic censorship. So is this the direction of your black hole in a cavity? Can you gain some insight also on cosmic censorship with your quantum version of the physics?
I mean, to be honest, that's not something that I've considered personally. I know with regards to Reiser-Nordstrom ADS spacetime, that there's been some recent studies on it. And I think one of the papers is cited by us where they've constructed the unroot state in Reiser-Nordstrom ADS spacetime. But apart from that, I don't.
But it's still somehow an uncharted territory on the quantum side, because on the classical side you can have instabilities and they're studied, and also you have interesting counterexample to cosmic censorship. So maybe it can be also interesting and look at the quantum side of it.
Yeah, that definitely sounds interesting.
I have a last comment if no one else has other questions. That is regarding the you were showing I think is equation 36. You were showing a specific radius where that should be independent, exactly. That should be independent of the charges. I mean, I guess from what I understand.
Scalar field charge.
From the scalar field charge, perfectly, yeah. So that's entirely dependent on the background, right?
Well, that's what equation 36 would seem to indicate. But when we looked into this phenomenon, we actually found that there is a slight variation in the scalar field charge. So I'm not sure how that enters into the equation, or whether this equation is. I think it would probably enter through the constants K and L, the flux of charge and energy, but there is a small dependence on the scalar field charge.
Okay, but the level of okay, but it still slightly changes. I was wondering if you can connect this specific value with, for instance, I don't know, the lightning of the background spacetime, or some specific point that comes out from the geodesics of the background, because superradiance is still associated with the peak of the potential and the potential well, classically. So perhaps there might be a connection with this specific point and some point in the potential, in the effective potential where superradiance occurs.
Well, that's very interesting. I can't say that, at least for me personally, I've thought of it in that way, but that's certainly something I'd want to look into, whether we could connect those two things. No, I personally haven't thought of that. I should quickly say that when I was the person I was mentioning that we discussed with about the Bowler and the putative Bowler light and Hartle-Hawking light states that we discussed was Bernard K. And we thought that since we defined these states with non-standard commutation relations, they might violate the K-Ward, a generalized version of the K-Ward theorem, which would hold for charged scalar fields. Yeah, apologies, I forgot that in while doing the presentation.
Don't worry. Okay, so if there are no last comments, I would
just like to congratulate Viz for this very nice seminar. My internet was not perfect, but from what I could follow, I enjoyed very much this seminar by Viz, as usual. Seminars given by Viz, and I have enjoyed very much the questions. Very interesting. Thank you very much. Thank you, Viz.
Thank you, Luis.
thank you very much. A round of applause for our speaker. And we hope to see you soon in Aveiro. And thank you very much for being here to everyone. We see you next week.
Thank you. Bye, everyone.
Bye-bye.
See you.